Hey guys, this is Mrs. Harbin, and this is Algebra 2, and we are looking at section 2.6, Graphing Inequalities. We have been talking about all kinds of functions and linear functions and piecewise functions and absolute value functions. So today we're going to look at inequalities and what those look like when we graph them. Our life application for our unit is this. The student will seek out healthy relationships with people that will promote godly behavior and encourage one another to lead wholesome, pure lives according to God's plan for each of us. We've been talking about how linear equations and the different functions represent relationships between x and y, and that's a good reminder that we were made to be in relationship with one another, and you can't live by yourself, you can't function by yourself, you have to be in relationships with other people, and we encourage you to seek out healthy relationships. We also need to understand mathematical relationships so that we can explain things in nature and science and take care of creation and take care of people. Our lesson objective for today is you, the student, will graph linear and absolute value inequalities. So any line in a plane divides the plane into three sets of points. You have the line itself, which is called the boundary, the top half of the plane, and the bottom half of the plane. Taking this out of the realm of mathematics, if you draw a line across a sheet of paper, you're going to have the top half of the paper, the line itself, which is the boundary, and then the bottom half. We see this all throughout. When we look at the equator, we have the northern hemisphere and we have the southern hemisphere. So you see this in lots of different places where you have the line itself and then the top and bottom half of the plane. Now, in an equation, when there is an equal sign, we know that x equals y at those given points. But when the equal sign in a linear equation is replaced with an inequality, the solution to the resulting linear inequality includes all the points in one of these half planes, either all the points that are greater than or all the points that are less than. Previously, it just included, our solution was just the points on the line, just the points on the boundary. But now we're looking at several possible solutions. A solid line is used when the inequality is less than or equal to or greater than equal to. You'll remember when we were graphing these on a number line, when it was less than or greater than equal to, we had to have a solid colored dot closed in. So when we're doing this on the Cartesian plane, it's going to be a solid colored line to show that those points are included. It indicates that the points that are on the boundary on the line are in fact solutions. A dashed line is used when the inequality is less than or greater than. On a number line, we use an open circle to show that point was not included. And when we see this on the Cartesian plane, we will see a dashed line. Let's take a look at this example. Let's graph x minus y is greater than or equal to negative 2. First, we're going to go ahead and put this in slope-intercept form, the same as we have been doing for the previous 5 lessons so far. And when we move that x and divide everything by negative 1, we get y is less than or equal to x plus 2. In case you're not following what happened there, we subtracted x from both sides, so that gave us negative y is greater than or equal to negative x minus 2. But I don't want a negative y, that's a negative 1y, so I'm going to divide everything by negative 1. Well, dividing by a negative not only cancels that, it changes our signs and it flips our inequality sign. So we get y is less than or equal to positive x plus 2. So that's where that equation came from if you weren't following those steps. After we have it in slope-intercept form, we can identify the slope, which is 1, and our y-intercept, which is 2. And graphing that on the Cartesian plane, we're going to plot our y-intercept here and our slope of 1. Then we'll use a straight edge to connect the dots, which they have already done for us. Because this is less than or equal to, we've got to have a solid line, not a dotted line. And then we have one final step. We say that y is less than or equal to x plus 2. So there's a couple of ways that we can do that. We can do this, I'll give you the longer way and then the shortcut way. So first, we're going to use a convenient point, such as 0, 0, to determine which half of the plane has the solutions and should be shaded. So when we plug in 0, 0 into our equation, we get 0 is less than or equal to, greater than or equal to negative 2. That's true. which means this 0.00 should be included in our solutions because it is a true statement. So we're going to shade the bottom half of the part under the line. Okay, a little shortcut to remember is since y is less than the graph, we shade downward. If you think of this maybe like a mountain or a hill that you're climbing, anything greater than, you're going to shade the upper portion or the sky here. If we're climbing a mountain, that's the sky. And anything that's less than or equal to, we are going to shade below the mountain, and we'll shade underground. I don't know if that will help you remember that, but it helps me. Less than, we go under the line, and greater than, we're going to go above that inequality line. Some similar methods can be used to graph other inequalities. First, we want to graph the boundary using a solid or dashed line, depending on the sign, and then shade the region that contains the solutions. Greater than will shade up, and less than will shade down. Let's take a look at this in action in a real-world problem. The athletic department is attempting to raise $600 by selling t-shirts and sweatshirts that show the school mascot. They make $4 on each t-shirt and $10 on each sweatshirt. Write a linear inequality modeling the funds raised by the sale and graph the inequality. Well, we know that they want to make at least $600, so they want to make either greater than or equal to $600. By selling a certain number of t-shirts, we don't know how many, for $4 each, and a certain number of sweatshirts. We don't know how many, for $10 each. Writing that as an equation, we get 4x, or $4 for each t-shirt, plus 10y, $10 for each sweatshirt. When we combine those together, we want to get an amount greater than or equal to 600. Let's go ahead and graph that. We're going to put that in y equals mx plus b, which gives us this equation. Our slope is negative 2/5, that's that direction, and our y-intercept is 60, so way up on the top of the y-axis there. When we put that into a graph, here's what we get. We're in quadrant 1 only. Because we're talking about a real-world problem, we're not really concerned with negatives, or negatives. We want to make money, not lose money, so we're just going to stay in quadrant 1. We know our y-intercept is 60. And then our slope is down 2 and over 5, down 2 and over 5, down 2 and over 5. By looking at this graph, we can answer many, many questions. We can see all the different combinations of t-shirts and sweatshirts in order to get above $600. For example, you can see that when we sell 50 t-shirts, we have to have 40 sweatshirts sold in order to make $600. Or when we sell 100 t-shirts, we need to sell 20 sweatshirts to make over $600. So this can give us a good estimate, help us establish a sales goal to meet our fundraising goal. Taking a look at that graph, what's the minimum number of sweatshirts that need to be sold if they have 9 dozen t-shirts? Well, we can write that in equation. 4x plus 10y is greater than or equal to 600. 9 dozen t-shirts, that's 9 times 12, so 108. So $4 times 9 dozen t-shirts plus 10y is greater than or equal to 600. And when we solve for y, they need 16.8 sweatshirts. Well, you can't really sell 16.8 sweatshirts. Can't sell an 8/10 of a sweatshirt. So they need to sell at least 17 sweatshirts. If we go back to our graph here and look at 108 t-shirts. Let me back up a little bit here. Let's see, we've got 108 is right around here, probably. Okay, so we can look at this to estimate. It's a little bit less than 20. And we know that by plugging it into the equation, we find the exact number of 16.8 or at least 17 sweatshirts. Today we worked on these things. We graphed linear and absolute value inequalities. We actually did not do absolute value. So we graphed linear inequalities today. We did absolute value equations last time, and we'll do absolute value inequalities together in class, but they are not presented in this video. If you have any questions, be sure to ask me next class.